Okay, today we'll do the review for the fourth test, which will be just over Chapter 4. You do have to finish Chapter 5 also, but that'll only be on the final exam, and I'll do another review video for the final. But today, Chapter 4, I found 18 similar problems in the review as that are on the test. And as I emailed out, the first one is 4a, determine whether each function is one-to-one and explain your reasoning. F of x equals 2x to the third plus 6. So one way to check for one-to-one is by a graph. You could use a graphing calculator if you don't know how to graph 2x to the third plus 6. But we also learned in an earlier chapter that the plus 6 shifts the graph up 6. The 2 is a vertical stretch and makes it a little thinner than normal. Otherwise it has the same shape as an x to the third graph. So this is what 2x to the third plus 6 looks like. We previously learned that if you use the vertical line test on a graph and you can't touch the graph more than once anywhere, then it is a function. There's also an idea known as the horizontal line test. There's no horizontal line on this graph that I could touch the graph twice with. So this graph passes both the vertical line test and the horizontal line test. When that's the case, then you can say the function is one-to-one. A one-to-one function is kind of like saying that to be a function you can't have any of the x's repeating. To have a one-to-one function, neither the x nor the y can repeat. So if you pass both the horizontal and vertical line tests, your x's or y's, none of them will repeat. This is yes, one-to-one, passes both the vertical and horizontal line tests. The reason that's important is if a function doesn't pass the horizontal line test and it's not one-to-one, then it would turn out if you found the inverse of it, that inverse would not be a function is the problem. So when we're going to find inverses here in a minute. When we find an inverse, we need it to also be a function, and one-to-one assures that, and using the horizontal line test can assure that that's the case. So that's 4a. Second problem is 5a. Use the definition of inverse function to determine whether f and g are inverses. So they give us two functions. F of x is 3x plus 9. G of x is 1/3 x minus 3. To test if they're inverses of each other, you have to do two things. First, you find f of g of x, which is from an earlier chapter as well. F of g of x, that's where you take g of x, the entire function, 1/3 x minus 3, plug it into f's function where the x is. So right, you got that 3x plus 9. Right where the x is, you're going to plug a 1/3 x minus 3. So now it's 1/3 x, 3 times 1/3 x minus 3 plus 9. Just the g function took the place of the x. Simplify that out by distributing the 3. 3 times 1/3 x would be 1x. 3 times negative 3 is negative 9, and you still have the plus 9 there. So then the negative 9 and the plus 9 cancel out, and it leaves us with just x. And that's what you hope happens if you want to have inverses. Now, to really prove it, you have to also do it the other way too. We have to now take g of f of x, stick f of x into g. Take this 3x plus 9 that f's equal to, plug it into the x of g's function. So it's 1/3 x minus 3, so we're going to have 1/3 all that stuff minus 3. Then do the same thing, distribute 1/3. 1/3 times 3x is x. 1/3 times 9 is 3. There happens to be a minus 3 there, luckily. So that way the x's cancel, the 3's cancel, and we're left with just x. If you do both of these composite functions, f of g of x and g of f of x, and if they both equal x alone and everything else cancels, then you can say yes, they're inverses of each other. If you get anything but just x, even if it's just x plus 3 left or 2x is left, then you'd have to say no. So that's the second question, 5a. Third question is like 6b. 6b. Now, instead of giving me two functions and asking are they inverses of each other, they give us 1 and say find the inverse for each 1-to-1 function. Now they are mentioning that it's 1-to-1, so that means when we find it, it actually will be a function itself too. So the given function is 4x minus 3. Kind of a multi-step process to find an inverse of a single function. Take your single function f of x equals 4x minus 3. First thing is that y is the same thing as f of x. So we're just going to replace f of x with y. Y equals 4x minus 3. F of x and y can be interchanged all the time. We like to use y when we're doing graphs, and we like to use f of x when we're plugging numbers in. So then, here's what the definition of an inverse is. An inverse is when the x's and the y's switch places with each other. Everything's reversed. So we put the x where the y is, and we put the y where the x is. X equals 4y minus 3. Now you just solve for the y. Get the y by itself again. So I can add 3 to both sides. X plus 3 equals 4y. Divide both sides by 4. Once the y is by itself, that's in essence the inverse then. The inverse of our function is x plus 3 all over 4. So to denote that it is definitely the inverse of it, we change the y back to a function notation, and we specifically call it f inverse of x. The notation is, it looks like a little -1 exponent, but it's read f inverse of x. Then you specifically know it's definitely the inverse of f of x. Here's f of x, 4x minus 3. The inverse is x plus 3 over 4. And if you took both of these functions and did what we did on number 5a, we could do this all over with both of them, and they would both equal just x. And that would also show that they're inverses of each other. But you won't know that till you get to the answer is the problem. So there's the process for finding an inverse when they give you one function. Okay, move down to number 11. 11, A, B, and C are the next 3 problems. Solve each equation. These are what are called exponential equations because now the base is a number and the exponent has the variable. And in an equation of these kind, the first goal, if you can do it, and you can't always do it, but if you're able to do it, you want to get the bases to be the same. 1/3 raised to the x plus 1 equals 9 to the x. 1/3 to the x plus 1 equals 9 to the x. Well, I can change 1/3 to be 3 to the -1. That's what a negative exponent does. It makes the base move to the other half of the fraction. Or, as the more familiar way you're probably used to seeing it, 3 to the -1 is the same thing as 1 over 3. And the reason I did that is I noticed that 9 was 3 squared. That way both bases are 3. That's the biggest thing you got to be able to do, is get both bases to be identical. They got to be identical in every way. You can't have one where there's a 3 and the other one where there's a 1/3. That's not the same. So they got to both be 3s. And then, now that we have them, we have like an exponent raised to an exponent right there. That's a rule of exponents from an earlier algebra class. And that's the rule where you multiply the exponents. 3 squared to the x is 3 to the 2x. It's not 3 to the 2 to the x. You don't do it to an exponent, you multiply the 2. 2 times x is 2x. And here you multiply the -1 to both x plus 1. -1 times x is -x. -1 times +1 is -1. So that's where you want to be, is where both sides of the equation have the same exact base and the exponents are settled. So now we can cross out the bases in essence. The bases cancel each other out. If the bases are equal, the exponents must be equal. So we set the exponents equal to each other and solve for x. -x minus 1 has to equal 2x to make the exponents equal each other. Add x to both sides and you get 3x equals -1. Divide by 3. X equals -1/3. (11b) has a base of 5 and a base of 25. So this one's a little bit easier to get started because we don't have to change the 5. We can make 25 look like a 5. That's usually the goal. Try to make the bigger number look like the smaller one. You can't make bases bigger, but we can make them smaller by turning them into powers. 25 is the same thing as 5 squared. So I've got 5 to the 3x plus 6 equals 5 squared to the x minus 3, because 5 squared is the same thing as 25. And then I can do the multiplying exponent rule. The 2 gets multiplied to the x and the negative 3 to make 5 to the 2x minus 6. And that will be equal to 5 to the 3x plus 6. Once the bases are the same and you got the exponents situated, then cross out the bases and set the exponents equal to each other. 3x plus 6 has to equal 2x minus 6. Then it shouldn't be too difficult to solve for x. Here I subtracted both sides 2x, leaving x plus 6 equals negative 6. Subtract 6 from both sides, and x equals negative 12. The final one on number 11 is 11c. X to the 3 halves equals 27. So this one's a little different. This is not exponential because the x is in the base this time. So this is just about trying to get the x by itself. We have to get rid of that 3 halves exponent. The opposite of a 3 halves exponent would be a 2/3 exponent, because then you'd multiply the exponents. 3 halves times 2/3 would be 6 over 6, which equals 1, and then the x would be x to the 1, and in essence x would be by itself. So the step here is to multiply or raise both sides of the equation to the 2/3 exponent. The x will be by itself now, and then we can change a fractional exponent. This is another thing taught in an earlier math class. Fractional exponents can be radicals. So 27 to the 2/3 can be the cube root of 27 squared. The divided by 3 is what becomes a root. The divided by 3 becomes the cube root of 27. And then you can still square it. And it works both ways. You can do the cube root first and then square that answer, or you can square the number first and then take the cube root. It's usually easier to do the root first because it'll make that value smaller. If I try to do 27 squared, it's going to be a gigantic number. But the cube root of 27 is 3, and then I can just do 3 squared. And then therefore the final answer is 9. Okay, scoot down to number 16a is the next one. Now, after exponentials, the next section in the chapter 4 deals with something called logarithms, logarithmic functions. Solving a log has 3 parts. You write log for log, it's short for logarithm. There's a little subscript base, so that's read log base x of 3 equals negative 1. So there's 3 parts of the log. There's that little subscript x, the 3 is in the domain slot, and the negative 1 is in the range slot. Another thing I always tell classes is a log is basically an exponent. There's rules of exponents kind of apply to logs as well. So if you say to yourself, a log is an exponent, the is equals. A log is an exponent, so therefore the exponent is negative 1, because that's after the equal sign, is an exponent. Negative 1's an exponent. This is read out loud, log base x. So what I'm going to do is turn this log statement into an equivalent exponential statement. Log base x of 3 equals negative 1. The x is the base, because we read it log base x. A log is an exponent, so the negative 1 is an exponent. So I always just say, okay, which one's the base? X is the base. Which one's an exponent? Negative 1. Clearly, the exponents are written up high. And the only thing I haven't used yet is the 3, so then it equals 3. So there's a number of problems in the homework where you have to take a log statement, turn it into an exponential statement, or an exponential and turn it into a log. You can always go back and forth between the two. Here it's easier to go to the exponential statement because then we can get x by itself more easily. X to the negative 1, there's that negative exponent rule again. That's going to change it to 1 over x. And I can make the 3 become 3 over 1. Cross multiply and solve for x. 3 times x is 3x. 1 times 1 is 1. Divide by 3, and x equals 1/3. That was 16a. 16b is similar, except here the x was in the base, now the x is in the domain slot. So they can really put the x anywhere, in the domain, the range, or the base. But the process is done the same way. I've got my three parts of a log. A log base 4 of x equals 3/2. Log base 4, so that means 4 is the base. A log is an exponent. The is where the equals is found, and then you see the number there is 3/2. A log is an exponent, so the 3/2 is an exponent. So I write the 4, the base is 4, the exponent is 3/2, 4 to the 3/2 equals x, because I haven't used the x yet. And x is already by itself, so to get the answer, all we have to do is evaluate this fractional exponent. That's the kind, again, where the denominator is the root. So we want the square root. And in square roots, they don't put a number in the little notch. It's just blank. In a cube root, you put a little 3 in the notch. In a square root, you just leave it blank. Square root of 4 to the 3rd power. It works either way. You can do the square root of 4 and get 2, and then do 2 to the 3rd and get 8. Or you could do 4 to the 3rd first and get 64, and yes, the square root of 64 is also 8. It works both ways. But I like to make it smaller. Square root of 4 is smaller than doing 4 to the 3rd. It just keeps the numbers smaller, easier to do. Answer is 8. The only issue you got to watch out for when you do these problems is if x is in the domain slot, the domain of logs is from 0 to infinity, not including 0. So you can get any answer in the range of a log. A log can be positive, 0, or negative for its final answer. But you can only plug in positive numbers, and the base has to be positive too. So sometimes you solve these equations and you get x equals negative something, and then that's impossible. So then we would cross that answer out. But x is here is the domain slot. The domain has to be positive, and luckily we got a positive 8, so this answer is fine. X equals 8. So you just got to be careful when you're solving log equations. Make sure a domain is never 0 or negative when you get your answer. Jump down to 20b. Okay, there's some properties of logs where you can take a single log expression and expand it out to multiple logs, or they do the reverse and they give you a long string of logs and they want you to condense it down to a single one. So the next two problems are actually reverses of each other. First, we have a single log that we're going to expand out into multiple logs. And the three main properties of logs is if you have a product, you can turn it into a sum. A quotient can turn into a subtraction. And then exponents can kind of slide up and down. So log with no base, when the base is blank, it's a 10. That's called common log. Common log of cube root of this big fraction with variables and exponents. So one thing I did first was the cube root's kind of in the way, so we could change that cube root to a fractional exponent. That's kind of the reverse of what we've been doing previously. So now it's log base 10 of this big fraction raised to the 1/3 power. And the reason for doing that is once you have a 1/3 exponent, the third property of logs is an exponent attached to the domain can slide down in front of the log and get multiplied to the log. It's one of the three main properties of logs. Or if you have a number in front, multiplied to a log, you can raise it up as an exponent. The property works both ways. Sometimes we go one way, sometimes we go the other. Here I want to get that 1/3 out in front just to get it out of the way. Now I can employ the other two properties of logs. When you're multiplying two things together in the domain of a log, you can write two separate logs added together. So a single log of m to the 5th times n to the 4th can become log of m to the 5th plus log of n to the 4th. One log multiplied together can be two logs added together. It's one of the three main properties of logs. And division works the same way, you just subtract instead of adding. So this divided by t squared gives us a third one where it's minus t squared, minus log of t squared. And you still have that 1/3 in front. Then just kind of one last step here, because all these log expressions still have exponents, we can use that third property of logs and slide the exponents down. So first you have a 1/3, then a parenthesis, then the log m to the 5th can be 5 log m, where the 5 comes down and gets multiplied in front. Plus log n to the 4th, that can be plus 4 log n. Minus log t squared, that can be minus 2 log t. So you're not really solving for anything here. It's just manipulating this using the properties of logs to write it in a different version. And you can go from a single log to 3 separate logs. Or, as in the next problem, you go from 3 logs to a single log. In 21a, it's log base b of p minus log base b of q minus log base b of r. So you can do it all together if you want, but here it is a little slower. If you just have 2 logs subtracted, you can convert that to 1 log divided. That's exactly the reverse of what we just did on the last problem. 2 logs subtracted is equivalent to 1 log divided. Then I could repeat it. Here's 2 logs subtracted, so I can make that 1 log divided. And literally it would be the first domain, p over q, divided by the second one, r. Literally p over q divided by r. So that kind of looks messy. We don't like to leave fractions inside of fractions. So think of the r as r over 1. Treat this like log base b of p over q divided by r over 1. And then there's a little expression I like to say, when dividing fractions, don't be shy. Flip the second fraction and multiply. So we're doing the reciprocal of the denominator, just so that we don't have fractions inside of fractions. By multiplying both the top and bottom by 1 over r, the entire denominator cancels out. And p times 1 is p, q times r is qr, so you literally get p over qr. So I was able to take 3 separate logs that were all subtracted and condense it down to a single log that's divided, basically. And kind of a shortcut to all this, too, is if you have a minus log, minus q and minus r, anything that's minus ends up in the denominator. The front log is basically positive, so then it ends up in the numerator. The p's in the numerator because it came from a positive log. Q and r are in the denominator because they're from negative logs. Okay, jump down to 25. Here's 2 kind of easy ones if you have a calculator that can do this. Use a calculator to evaluate each log to 4 decimal places. And the point of this is they want to teach you about common log and natural log. A base of a log can be any positive number, so there's literally an infinite number of bases. But there's 2 special ones. If you have base 10 is called common log. And it's the most common one to the point where they don't even write the 10. If you don't see a little subscript on a log, it's automatically a 10 for the base. The same way square roots never write the 2, or x's, you don't write 1x, you just write x. It's the same deal. Everything's got a blank version. So log base 10 is common log. ln is short for log base e. That's natural log. E is that special constant in math, 2.54. Kind of similar to pi, but it repeats a little bit more. So log 34.56 or ln 34.56. Most calculators have a log button and a ln button. My calculator has them right here and here, log and ln. There's too many bases for a calculator to put all the bases on here because there's an infinite number of positive numbers. So most just have log and ln. So I can hit the log button and type 34.56 and it'll give me a long decimal. It's kind of like hitting a square root in a calculator. If you do the square root of 2, it'll just give you a long decimal. So log of 34.56 is 1.53857. If you stop at the 4th place where the 5 is, there's a 7 after that, so we have to round that up to 1.5386, which is the answer to 25a. 1.5386. Do the same thing for B, natural log of 34.56, and this is kind of a good side-by-side. The answer is quite different. It's 3.5427 as opposed to 1.5 because the base is different. One's got a base of 10, the other one's got a base of about 2.5. So if you hit ln 34.56, again a long decimal, 3.54269. So the 9 is going to bump that 6 up by 1 and make it 3.5427. That's 25A and B. Next is 29A. Now, because of the fact that we only have log and ln buttons on our calculator, there's a change of base formula that can let you write a log of some other base, like here's log base 3 of 11. We don't have a log base 3 button in our calculator. So we can convert this so it can be log base 10 or natural log base E. In fact, 29A asks you to do common logs, 29B asks for natural logs. And all you do, and this works for any base, you could use another base like base 7 if you want, but we just don't have a calculator button for that. So log base 3 of 11, it can be either log base 10 of 11 divided by log base 10 of 3, that's common log, or you could do natural log and do ln of 11 over ln of 3. So the 11, which is higher up in the domain slot, that goes higher up in the fraction. The little 3 subscript, that's down low, so that's why that goes in the denominator. That's easy to remember, that the one that looks like it's higher up in the problem, that's the one that goes higher up in the fraction. It's not necessarily the bigger number in the top. If I wrote log base 11 of 3, then I would put log of 3 on top and log of 11 on the bottom. And it doesn't matter which way. This question just wants you to state what would it look like. So the answer is literally log of 11 over log of 3. They're just trying to have you employ that change of base formula. But often we do this to get the answer, and notice that the answers are the same. Whether I put them in the calculator as common log base 10, or if I use natural log base E, you get exactly the same answer, 2.1827. They didn't want that answer here, but if you come in your calculator and hit LOG, hit the log button, hit 11. Now when you hit log, a parenthesis pops up. So it helps to close the parenthesis first, then hit divided by, hit the log button again, 3. Log 11, close parenthesis, divided by log of 3. It turns out you don't have to close the second parenthesis because we're not doing anything else after that. 2.18265. If I do it with natural log, ln 11, close parenthesis, divided by ln 3, exactly the same answer. They're both 2.18. And that's what we want to do, is we want to change either to common log or natural log because we have calculator buttons for those. So that's the point of those two problems. 29A was that, and I just did both of them, even though it only wanted 29A. Let's go to 31, part A. Here's where this gets used, actually. Remember those problems earlier where we had 5 raised to something equals 25? And we could turn the 25 into a 5 squared to match the base? You can't always do that. 4 to the x equals 12. There's no way to make 12 look like a 4. 4 squared is 16, so it's already too big. You can't even change the 2's. 4 is 2 squared, but there's no base of 2 that equals 12. So in some of these exponential equations, you get stuck where you can't make the bases the same. So we can still approximate the answer, 4 to the x equals 12, if we put a log on both sides of the equation. I'm going to use common log. You can really use either one, but I use common log anytime the base is a number, and I use natural log anytime you have e involved as a base. So the same way you can take a log off each side when they're both there, you can insert a log on each side of an equation. You haven't changed it then because you've done the same thing to both sides of the equation. Log of 4 to the x equals log of 12. The purpose of doing that is now I can use that property of logs where the exponent can come down in the front. And I can have x times log of 4 just sliding the exponent down because we're trying to get the x by itself. Log of 4 has some decimal version of an answer, kind of like square root of 5 is just a decimal. So I can divide both sides by log of 4. And this is kind of like the change of base formula. X equals log of 12 divided by log of 4. Then you could just punch that into a calculator and get an approximate answer. X equals log 12 divided by log of 4. Approximately that's 1.7925 using a calculator. So inserting a log to both sides of the equation, that can get the x out of the exponent. And then you just solve for x as normal and get a decimal version of the answer. That was a good one to do when the base had a number in it, where the base is 4 to the x. In 31c is the next one. There's a base of e this time. 2e to the 5x plus 2 equals 8. Well, first that 2 is kind of in the way. 2e to the 5x plus 2 equals 8. I can definitely divide both sides by 2 first. Let's just get the 2 out of the way. And we can have e to the 5x plus 2 equals 4. So to get the x out of the exponent, all you're going to be able to do, we can't make both of the bases the same. There's no way to make 4 look like an e or vice versa. So I got to put a log on each side of the equation to get that x out of the exponent. And here's the time, since the base is e, use ln instead. Don't use log, use ln when the base is e. Put an ln on both sides of the equation. Then you can bring the 5x plus 2 down. But ln of e actually cancels out. Ln of e are opposites of each other. They're inverses. The log and an exponential are inverses. So ln of e basically cancels out. And you just get the 5x plus 2 left. That's the reason to pick ln for that kind of problem. So now you're left with 5x plus 2 equals ln 4. You can figure out ln 4 with a calculator, 1.3863 approximately. Then you're just solving for x. Minus 2 gives you negative 0.6137. Divide by 5 and you get 0.1227, negative 0.1227, which is the answer. So the two previous problems, we either put log on both sides of the equation or ln. That lets you get the x's out of the exponent. If the base is a number, use log, common log. If the base is e, use ln, because then ln and e will cancel each other out. Okay, we've got 3 problems left. Here's 3 solving log equations. Starting with 32b. Log of 2x plus 7 equals 0.25. It's really hard to see the point, but there's a point there, 0.25. And it's log with no subscript, so that makes it common log base 10. So log of 2x plus 7 equals 0.25. What I did is I changed the 0.25 to 1/4. It's just decimal's not going to help us much here. Log of 2x plus 7 equals 1/4. So now I'm going to use that strategy of changing a log to an exponential. The 3 parts of a log. Grab the base, grab the exponent, and then set it equal to the other part. Common log, even though it's blank, is considered to be a base of 10. So my base is 10. A log is an exponent. The exponent is 1/4. So I'm literally going to write 10 to the 1/4 equals the part I haven't used yet, 2x plus 7. All that is changing from a log to an exponential like we did a couple of times earlier in the review. Now you're solving for x. We can change 10 to the 1/4. We've done this already too. Change that to a radical, the 4th root of 10. You can get a decimal version of the 4th root of 10 in your calculator. I'll show you that in a second. But first I subtracted 7. Then I divided by 2 to get x by itself. X will equal, this as a decimal is negative 2.6109. The 4th root of 10 minus 7 over 2. So if they wanted an exact answer, we'd leave it like this, but if you want a decimal version, you can do this in your calculator. In the calculator, if you want to do fourth root, there's not a direct button for that. Let me clear all this off the screen. Okay, to do a fourth root, you actually type the number 4 first. Type a 4, hit the math button. There's a built-in cube root on the fourth choice, but there's a fifth choice that says X root. So if I go to the fifth one and select that one, it doesn't look like it. It looks like 4 times the radical, but this is the calculator's way of knowing, okay, I'm going to stick a 4 where that X is. This tells it to do the fourth root of 10. The fourth root of 10 as a decimal is here. Then you can finish it by minusing 7 and divide by 2. There's that negative 2.61086. So the 6 will bump the 8 up to a 9. Negative 2.6109. Negative 2.6109. So all I did was type that in the calculator. The fourth root of 10, then hit minus 7, then divide by 2, and that gets the answer. That was a single log equation. Now what if you have 2 logs added together in 32C? 2 logs added together equals 1. Well, we never want to have multiple logs while we're working an equation. So I'm going to do like we were doing previously. Take the 2 logs that are added together, condense them down to a single log. The property of logs. 2 logs added together is the same thing as 1 log multiplied together. So log base 5 of these two domains multiplied together, now that equals 1. Now some of these equations, you get a log on both sides of the equation, kind of like number 32, there's a log on both sides of the equation. That makes the ending of this a little faster. But if you only have 1 log, then you have to do the transformation to exponential version. Log base 5 of this product equals 1. So the base is a 5, a log is an exponent, the 1 is the exponent. So I'm just writing the exponential version. 5 is the base, 1 is the exponent, and equals the other part. So now it becomes an algebra problem that we actually did back in chapter 1. This is solving for x like back in chapter 1. 5 to the first is 5. You can FOIL out this binomials multiplied together. 3x times x is 3x squared. 3x times negative 1 is negative 3x. 2 times x is 2x, and 2 times negative 1 is negative 2. I subtracted the 5 just to get it equal to 0. 3x squared, combine the like terms, negative 3x plus 2x is negative 1x, and the negative 2 minus the 5 will create a negative 7. Now usually, when you reach this point, usually this quadratic would factor, and you could get 2 answers by factoring it, just based on the numbers that were given in the problem. It turns out this one doesn't factor, but just like in chapter 1, we can solve any quadratic with the quadratic formula. So you may not have to do this much work on a test question, but this is what happens here. I'm going to do the opposite of b. Opposite of negative 1 is positive 1. Plus and minus square root b squared minus 4 times a times c. All over 2 times a. Work out the inside of the radical, and you'll get it down to 85. So we've got 1 plus and minus the square root of 85 over 6. I just use a calculator for this because they just wanted decimal answers. 1 plus the square root of 85 divided by 6 came out to 1.7033. 1 minus the square root of 85 divided by 6 was negative 1.3699. Notice I crossed that out because these x's are from the domain. The x's are in the domain of these logs. And remember, domains can't be negative. So if you plug the first answer 1.7 into these 2 domains, 1.7 times 3 plus 2 is definitely positive. 1.7 minus 1 is positive. So that answer is okay. But when you plug in negative anything, in this case negative 1.36, negative 1.36 minus 1 is negative. A log cannot have a negative domain, so that's why we have to cross that negative answer out. A lot of students forget to do that at the end. They miss it because they did everything right, got 2 answers, but one answer needs to be crossed out because it leads to a negative domain. It's not so much that the answer itself is negative. That can happen sometimes. It's when you get the answer, if you plug it back into the original problem, in the domain slots, those cannot have negative values. Okay, final question is a subtraction instead of an addition, and it's a little nicer that both sides have a log. So first we do the property of logs, where 2 logs subtracted can be 1 log divided. 2 logs subtracted can be 1 log divided. And then if we didn't have a log on this side, we'd have to change it to exponential, but here we don't have to. The same way we put logs on both sides to get x's out of exponents, we can take logs away from each side. Both sides have an ln, so we can just cancel them out. And we're just left with the domains. 6x over x plus 1 has to equal 4, or 4 over 1. So this one's easier to solve than the previous problem. You don't have to use quadratic formula, because we can just cross multiply now. 6x times 1 is 6x. 4 times x plus 1 could be distributed to make 4x plus 4. Subtract the 4x. 2x equals 4, divide by 2, and x equals 2. It comes out real nicely. So that's the 18 problems that you'll see on the test. You can take the test anytime next week, Monday through Friday. And there'll be this test plus a final exam is all that's left. So good luck. Email me if you have any questions.